So here's an overview of the tremendous diversity of data that we have in CEFC, because we have a lot of data from a lot of different places. So remember that our little region, CEFC, is part of a larger star-forming complex that happens to be in the galactic plane, by which I mean the plane of the Milky Way. So just by chance, there's a lot of survey data that happen to include our region. And it was one of the 12 regions specifically targeted by the YSOVAR program. So we have a variety of data that were obtained specifically in the context of YSOVAR. And the infrared really is the driver for what we're doing, but we have a lot of data over a lot of other wavelengths too. So remember that it's actually really good that we have a lot of data over a lot of different wavelengths, because the young stars that we're studying here have lots of interesting emissions at lots of different wavelengths. So we have the young, fully convective, fast-rotating star in the middle, and because it is fully rotating and completely convective, it is got big star spots. Now, I don't mean a couple percent of the surface of the star is covered in spots like our sun. I mean like 40, 50, 80% of the surface is covered in spots. And so you get really strong flares that produce lots of X-rays, lots more X-rays than an older star. And you have, in many cases, a circumstellar dust disk. And that dust is creating emissions in the infrared. The closer you get to the star, the hotter it gets. So near infrared, mid-infrared, far infrared, all coming from different places in the disk. And the disk is probably flared in most cases, and so in the optical you can get scattered light off of the flare of the disk depending on your the observing angle. And because the star is completely convective and rotating quickly, it has very strong magnetic fields. And the magnetic fields actually thread the disk and terminate its thought, the disk, at some distance from the star. And then the matter, the charge, because it's very warm close to this, relatively close to the star, the charged matter climbs up the field lines and crashes down onto the star. And depending on the field geometry, you can get shocks in spots or in rings or in patches, and that is creating an excess of UV as it falls onto the star. But you're also getting an excess H alpha from the stuff in the accretion columns. Now you can get H alpha just from the flares as well, but you can get a huge amount of H alpha from the flares if it's a big bright star, but you can also get H alpha from the matter in the circumstellar disk. So excess H alpha, suggestive of youth; excess X-rays, suggestive of youth; excess UV, suggestive of youth; and excess infrared, suggested of youth. And we have data in all of these bands, so that's good. So remember from the other movie, YSOVAR is a program that's used Spitzer to study the time variability of young stars, including in CEFC. And the reason we picked CEFC is because it's got a lot of stars over a small area, so you get a lot of targets in one field of view. And the stars are very embedded. There's a lot of dust, and we can't see through it from the ground in the optical very well at all. So you can really only monitor these things from space. Not a lot of people have yet done detailed work here, despite there being lots and lots of data. We are doing that detailed work. We're finding all of the good YSO candidates, because then we need that in order to understand what the YSOVAR light curves are telling us. So remember that Spitzer is in an Earth-trailing solar orbit, and it has on board 3 instruments: IRAC, which observes at 3.6, 4.5, 5.8, and 8 microns. It has an instrument called IRS, the infrared spectrograph. That's spectroscopy. We won't be using that. And then there's MIPS, the multiband imaging photometer for Spitzer, which has bands at 2470 and 160 microns. When we had cryogen on board, all 3 instruments were working, but now that we no longer have cryogen and can only passively cool, only the shortest 2 channels of IRAC work, so 3.5 and 4.5 microns, but they work really, really well. So there's potentially confusing references to all of these channels. So I will frequently move between them. So IRAC channel 1 is also IRAC 1 or I1 or 3.6 microns. Or if I'm talking about things in magnitudes, like in plots, color, and color magnitude diagrams, you use the brackets around the wavelength to denote the measurement at that wavelength as expressed in magnitudes. And so you have the same thing for IRAC 1, 2, 3, and 4, MIPS 1, 2, and 3. So we have 3 distinct sets of Spitzer data to use. We have mapping at all the IRAC and MIPS channels from when we had cryogen. Rob Gutermuth has processed this for us, but we also have the data from something called the Spitzer Enhanced Imaging Products, or SEIP. That project took all the cryo data that Spitzer took, all of it, in IRAC and MIPS, and made mosaics and did source extraction of the bright sources. So we can get the mosaics from SEIP at any time, but we have the photometry actually is coming from Rob. I don't think I have the mosaics that Rob used, but we have the mosaics that the SEIP produced. We've got the YSOVAR monitoring, which was just 2 IRAC channels, and that means observing many times over at least 40 days. I think for CEFC it's much longer than 40 days. And then for GLIMPS was a survey of the galactic plane, and it was also doing mapping. And by the time I got to this part of the galactic plane, there's just 2 IRAC channels left. And so they just did 2 IRAC channels, but they observed it at a different time than YSOVAR did. And because these stars are intrinsically varying, we need to keep track of all of these measurements because they may be different for the same star, and we need to include them in the SEDs where we can. So details of GLIMPS. GLIMPS did a survey of the plane of the Milky Way, and they originally started relatively small in the inner galaxy, but this works really, really well, and they're finding lots and lots of interesting things. So they've done all the way around, and then some, and by the end, of course, they only had the 2 channels of IRAC. So we're going to use one of the later releases from GLIMPS. So the remainder of doing the whole circle of the galactic plane was called GLIMPS 360. And so we're going to use data from that. And if for the aficionados, GLIMPS 360 delivered several different flavors of catalog, we're going to use the complete but less reliable archive catalog. And the reason we want to do that is because we want to get all the faint sources, but we're looking at each of these sources by eye. So it doesn't matter that they're less reliable because we're going to check. Remember that IRAC has 2 fields of view, not 4, but 2. IRAC 1 and IRAC 3 use one field of view. IRAC 2 and IRAC 4 use the other field of view. So for GLIMPS and the cryo era observations, it really doesn't matter because the original GLIMPS project and the cryo era just tiled the whole region with all 4 channels. And even for the later GLIMPS observation, they're tiling it with both channels. For YSOVAR, though, the 2 fields of view matter. And because we have many observations over a long time baseline, how much the field of view rotates with time matters. So since this matters a lot in terms of what data we have where and why the footprint of our observations looks like it does, let's explore this in more detail. So it's kind of a shame we don't already have a, professionally produced video demonstrating this, but this is what I can do. Here's my El Cheapo handy dandy Spitzer model. That's the solar panels. The light comes in here, and that's the communications antenna with Earth. So that's the sun. We're going to keep the solar panels always towards the sun. But if you're the Earth, it has to rotate like this to talk to you. So as it continues in its orbit, it's going to keep this facing the sun, and then it's going to have to rotate to talk to you. Okay? So at any given time, it only talks to us once every week or so, even every couple of days, depending on how much data it takes. But if that's going to stay pointing at the sun, when it's not talking to Earth, it can go anywhere in this plane. So we can observe anything in an annulus, a donut shape, that it can, rotating around this point. So if I'm observing something that's in the ecliptic plane, I can observe it for about a month before it moves enough in its orbit that it can no longer see that same target. But things that are up at the ecliptic poles, it can observe at any time because it doesn't matter where in its orbit it is, it can still go that way or that way. So for a target like CEFC, which is at a moderately high ecliptic latitude, it can observe it for much longer than 40 days, over a period of much longer than 40 days. But the field of view rotates with time. When you're in the ecliptic plane, the field of view doesn't really rotate over the 40 days. When you're at the ecliptic pole, it rotates a lot because it has to do the whole 360 in half a year. So it rotates a lot at the poles and really not at all in the plane. So this is a tool called Leopard, which was one of the very much earlier tools that we originally used to get data out from Spitzer. And it has a lot of the same tools in common with Spot, which is our observation planning tool. But the reason I'm showing this to you is because it's a visualization of the original cryogenic era observations obtained of our target. So let me hide the observations. That's FC. That's our target right in there. So this is the total sum of the observation. Let me show you what it looks like, how the spacecraft actually moved through. So it started up here, moved. You see how it's steadily moving over to cover the whole area. The magenta footprint is the 4.5 and 8 micron footprint, and the cyan one is the 3.6 and 5.8 footprint. Let me do it again, but this time we're going to leave a trail behind. You see it's going through and tiling out the whole region, and then it's going to go back and do it in a slightly different order at a slightly different position. The reason you want to do that is because if an object is real, it's really on the sky, then it doesn't move. But if it's a transient like a cosmic ray, then it will move between those different frames. So by doing that dithering, you have a better sense of what is an instrumental effect, what is a cosmic ray, and what is actually in the sky. So that's the final cryo-era IRAC map. So this one is going to be the cryo-era MIPS map. MIPS is a completely different instrument than IRAC, and it has actually in the end several different fields of view for the 3 cameras that it had inside. But for the imaging, there were 3 fields of view, one for 24, one for 70, one for 160. So the 160 field of view is the green, the blue is MIPS 24, and the pink is MIPS 70. And it had a mode that is used here called scan mode. Basically, the spacecraft is moving steadily over the sky, taking pictures as it moves along. And there's a little scan mirror inside the instrument that moves exactly at the right counter to the spacecraft motion so that the image is held still on the detector for the exposure time before it moves on to the next one. So let's do the animation of this. You can see that it starts at the lower left and is moving steadily up to the right. So remember, pink is 70, blue is MIPS 24, and we haven't seen any 160 yet. There's some 160 coming in. So you see it's taken a whole series of frames as it's moving along. So much like IRAC, where you want to dither, here you have a whole series of observations taken at slightly different positions for basically the same reason. If it moves with your detector, it's not real. If it's stationary in the sky, then it's real. So you see it's going to paint out this one long stripe. It's going to go all the way up to the top, and then the spacecraft's going to move a little bit, and it's going to come back, painting all the way back. Here it comes back. There's 160, there's the 24 coming in, and eventually we'll see the 70 coming in. Remember, our target is here. So you see it's painting this whole region, actually a much larger region than CEF-C, with the 24, the 70, and the 160 microns. For what we're going to do, we're only really going to care about the 24 micron data. The 70 and 160 micron data are cool, but we have Herschel data at those wavelengths, and Herschel is much better than MIPS when it comes to sensitivity and aerial coverage in those bands. So we're going to use Herschel for those longer wavelength bands. Okay, so we know that there's glimpse observations too. So it turns out glimpse, remember, is doing a survey of the whole galactic plane. So they are covering huge sections of it, and they're doing it in sort of puzzle pieces with individual observations that they, after the fact, combine into one big, tiles of mosaics. So remember, our little guy is here. So that tile gets close. Remember that we have the magenta is 4.5 and the cyan is 3.6. So then there's another tile there that also entirely covers our region. That one is not really covering our region. There is an adjacent one. So there's other tiles in here too. But much like the cryo-era observations, it's, making these huge mosaics out of lots of individual pointings. Okay, so now we're going to look at just the YSOVAR observations. Remember that the other programs that we looked at, the Cryo-ERA one or the GLIMPSE one, they're trying to tile over a huge area to create a continuous patchwork quilt of observations over the whole region. YSOVAR, by contrast, is trying to monitor just the stars in one region. So instead of getting a lot of area, we're getting a lot of time coverage because we're observing the same thing many times. So if I put on the animation here, so the region that we care about is here. So what it has to do is take data with the one field of view and then shift and take data with the other field of view. You see it's dithering just like the other observations, but we're really only covering with both channels that central region. Dithers and then it moves. And then in this, the cyan field of view is getting the target region here, and this is coming along for free, and that is coming along for free. So our target region is monitored in both bands, but at almost the same time, not quite, but almost. And then you get data for free over here and data for free over here. And we don't want to just throw out that free data. Just because the place where we have the most data is in the middle doesn't mean that data we got for free isn't good and good for science. So that's the first epoch of observations. That's the second epoch. See, it's just a little bit later, but it's enough that the field of view rotates. Remember from my handy-dandy Spitzer model from before, it is observing things in an annulus, and how much the field of view rotates is a function, with time, is a function of the ecliptic latitude of the target. And this thing is relatively high out of the ecliptic plane. So the rotation is pretty substantial. So between the second epoch there and the 10th epoch, you can see it's rotated a lot more. Let's add the 20th epoch, still further. 30th epoch, further still. Let's go to 54th epoch, big change. 144th epoch, we've rotated all the way around. You see, up until this point, the only field of view, the only ancillary data we were getting for free was in channel 1 over here. Now it's flipped around so that channel 2 is over here and channel 1 is over there. So when you have collected all the observations that we took for this entire campaign, you get data in both channels in the middle. And you get free data in one channel for quite a while, and then eventually catches around and gets data from the other channel. And the same thing over here. So the net result is sort of a fan of data coverage in which we have partial light curves in one channel for that ancillary data that's on the side. Okay, so to sum up, Spitzer can see at any given time an annulus on the sky, but that annulus moves with time. It can observe the ecliptic poles at any time for any length of time, but it can observe things in the ecliptic plane only twice a year for about 40 days each time. CEFC is pretty high up there. It's about 60 degrees ecliptic latitude, and so it can observe for longer than 40 days, but the field of view rotates a lot with time. And the YSOVAR data has two channels over the heart of CEFC, but lots of data that we got for free in just one channel on sort of a arc-shaped, fan-shaped wings around it. And that's what that net footprint is trying to show you. So there's CEFC in the middle. That blue and red purplish box there is the region over which we have both channels of observation for this one epoch here. We got the IRAC 1 data for free here, and then the IRAC 2 data for free over here. But then it's going to rotate with time. So the net final mosaic of IRAC 1 is shaped like this with these funny fans, and the net IRAC data, sorry, that would be channel 2 because it's blue. Sorry, no, channel 1 because it's blue. And then channel 2 being longer is in the red, and it's also got sort of a fan-shaped thing, but of course it's the reciprocal because the IRAC 1 and 2 fields of view cover slightly different places on the sky. In this figure, the yellow is the box over which we have Chandra observations. And so for our project, since in many cases we're looking at cones or squares on the sky, I've just asked for data over this whole larger region, even if we're just going to be focusing on the slightly smaller region. So here's the table from our proposal that has a list of all the existing data. There's Chandra, SDSS, IFAS, 2MASS, Spitzer, Spitzer WISE, Herschel, Scuba, YSOVAR, and H-alpha bright. Let's go through all of these with a couple of slides for each. So for Chandra is a satellite. It observes in X-rays. It is a pointed observatory, not a survey observatory. So it points where we tell it. It has cylindrical mirrors because if the photons just hit the mirror straight on, it would go through. So it has cylindrical mirrors so that the photon just kisses off the surface and gets focused on the detectors. It has a highly elliptical orbit, goes a third of the way to the moon. Our data come from something called the Advanced CCD Imaging Spectrometer, or ACIS. Chandra, it turns out, counts individual photons. So when you're looking at images, you want the event file, which ends in evt2.fits. The PSF, the way that the observatory responds to light, is a function of how close the source is to the center of the image. This is our data. You can see there's lots of sources in there. You can see the boundaries between the chips. This is an example not from our data, but from the official documentation of how the PSF changes. So this is the PSF close to the center of the field of view, and this is the PSF out on the edges. So the ellipse is pointing towards the center of the observation. So you end up with ellipses like this in the outer ring, all pointing in towards the center. Sloan is a survey taken from a ground-based telescope. It has mapped an awful lot of the sky, but not all of it. It does happen to run over our region. It observed in the optical, and then here's the specific bands and wavelengths. They really are all lowercase letters. I'm not being sloppy. It's UGRIZ at this wavelength in angstroms and this wavelength in microns. It does not use Vega-based magnitudes. In the other video, we talked a lot about Vega-based magnitudes. It uses AB magnitudes, and this is going to matter when we're converting from magnitudes to flux densities. But it's the only one of the surveys that uses AB magnitudes. Everybody else is in Vega magnitudes that we are dealing with here. IFAS is the INT photometric H-alpha survey of the Northern Galactic Plane, where INT is the Isaac Newton telescope. This is a ground-based survey. IFAS surveyed the galactic plane, which happens to include CEFC. This is the range of galactic latitude and longitude that it surveyed, and it surveys in 3 bands, R, I, and H alpha, and it goes down pretty faint. Sometimes people write R, because it is a little r, as R prime, because it's not quite the same as the Sloan bands, and it's Vega-based magnitudes too. So especially if someone is working with both Sloan and IFAS data, sometimes they use the IFAS, they refer to the IFAS filters as R prime, I prime, and H alpha. In any case, there are the wavelengths of light correspond to, and remember that H alpha is a narrow band filter. R and I are broadband filters, but H alpha is a narrow band filter. Go back to that movie to learn more about the bands and filters. But the point of this is that because it is narrow band photometry, it's going to pick out things that are bright in H alpha, which if you remember the anatomy of a young star, this is good. Remember that we also have H alpha bright stars from the literature, but it turns out there are only 2 in our region from the literature, which kind of surprises me. These are both optical observations, they're ground-based observations. There's one paper by the Mikami et al. Paper targeted this region. We don't have access to their images. It's the only one of these surveys that we don't have access to the images, and it found only 1 star in our region. And the other H alpha star comes from IFAS itself, because they published a list just of the H alpha bright sources that they found. 2MASS is the 2-micron allsky survey. It was conducted by 2 ground-based telescopes, one in the northern hemisphere and one in the southern hemisphere, and it observed the whole sky. It is a survey. It observes in the near-infrared, or NIR, at J, H, and K bands, so between 1 and 2 microns. At these wavelengths, we're starting to be sensitive to the infrared excess from the disks. WISE is the Wide Field Infrared Survey Explorer. It is in a sun-synchronous polar orbit. It is also a survey telescope. It observed in all 4 channels when it had cryo, and here we've got the nomenclature again. Sometimes it's WISE-1, W1, 3.4 microns, or with the brackets if you're talking in magnitudes, 4.5, 12, and 22 microns. Because there are budgetary issues, this telescope was operated for a while, then hibernated, then brought back. Now it's still operating under the name NEOWISE-R, R for reactivation, and its main mission really is to look for space rocks. There are many, many, many different image and catalog deliveries that it pays to sort out, which we'll do. The Herschel Space Observatory was at an orbit, an L2. That's really cool. It's a Lagrange point. You should go look that up if you're interested in orbits, because it's really cool. L2 is relatively crowded, and so when it ran out of cryogen, they kicked it out of the L2 spot so that other satellites could be there. It has a 3.5 meter mirror. For comparison, Spitzer is 85 centimeters, WISE is 40 centimeters. So 3.5 meters is enormous compared to those, and the reason it has such a big mirror is because it's observing at long wavelengths. It had 3 instruments on board: PAX, Spire, and HiFi. HiFi is spectroscopy. We're not going to use that. PAX has complicated observing modes, but it can observe anywhere between 6 and 210 microns, and Spire can observe between 250 and 520 microns. And this is a targeted observatory, not a survey observatory, but there are targeted observations of SFC that were never published. So that's what we're going to use. And then the longest wavelength we have is from Scuba. Scuba is the sub-millimeter common use bolometer array, which is obviously sub-millimeter instrument that was on the James Clerk Maxwell Telescope in Hawaii. We have detections in 2 bands, 450 and 850 microns. The light detection mechanics are very, very different here. I suggest if you're interested in detection of light, you should go look it up because it's pretty cool. Scuba data is seeing mostly the dust, and the data we're using come from a survey of star-forming regions, which is already published. So we've just pulled the point sources out of the literature, and they also made their images available online. So I have those as well. So all of these observations were imaging surveys. We're not doing the spectroscopy, we're just doing the imaging surveys. So all the images exist somewhere on somebody's disk, though we may not have the images on our disk right this second. The only one that we really don't have access to is the Mikami et al., but that's okay because it's only one band, only one object, and we already have the H-alpha data from IFAS. Now, I haven't pulled the images from IFAS, but I have pulled them from Sloan, from JCMT, from Chandra, from Spitzer, lots of different places. So we have a lot of data already on disk. All of the observations of the photometry are already done, except for possibly Herschel. I need to talk to the Herschel guys to actually get the photometry and the final images from them. I have downloaded the data from Herschel, the Herschel archive, and there's lots and lots of pieces to that. So I'm hoping that the Herschel Science Center can help us get the images and the photometry that they actually used for this region. I've already pulled the photometry. I've already done the position-based source matching. You should go watch the band merging movie to find out more about that. When we're using these data, because we weren't the ones that did the photometry, we really have to pay attention to the details of the catalog and the documentation that go with the catalog so that we can understand what they're telling us. Understand if the computer has confidence in the detection, if the computer thinks it's an upper limit or a good detection or a bad detection. We need to pay attention to all of those things, because at the end of the day, just because the computer says it does not make it right, you need to check. And we're going to do that. We're going to check and see if the merging of the catalogs makes sense, if the sources are really on top of each other in the images, or if there's a shift. We're going to do all of that.